Today we will be talking about total internal reflection. But first, I wanted to do a little bit of review. So remember, refraction is a boundary phenomena that occurs when a light wave approaches a new medium. Whenever light goes from one medium to another, it changes speeds. When it changes speeds, it changes direction. Now, the angle that we measure is always measured with respect to the normal line that's drawn to the surface. So I don't measure the angle from the ray of light to the surface. I draw a 90-degree angle with respect to the surface. We call that a normal line. And then we measure the angle from the normal line to the light ray. The last thing I want you to remember is this, that when light moves from a more optically dense material, that means it's moving more slowly, to a less optically dense material where it's moving quicker, it always bends away from that normal line. When light is going from a less optically dense material to a more optically dense material, it always bends towards the normal line. Now that's going to be important for today's discussion, because something strange can happen, when light goes from more dense to less dense. So if I'm looking at that light with my eye, I'm not going to look at the source of the light. I have to look where the light is changing direction to. Now, if I increase the angle from the more dense material, if I increase that angle of incidence, the angle of refraction gets bigger, so I have to move my eye. If I increase it enough, that angle of refraction can be 90 degrees. So in order for me to see that light, my eye would have to be at the boundary between the two surfaces. Now, what if I increase the angle of incidence very slightly from here? Can I have an angle of refraction bigger than 90 degrees? The answer to that is no. In order to have an angle of refraction bigger than 90 degrees, the light would have to be going back into the material that it came from. We call that reflection. And we have the law of reflection, where the angle of incidence is equal to the angle of reflection. So once again, if I make the angle just right, the light goes at a 90-degree angle of refraction and skims the surface. If I increase that angle of incidence at all, I move to reflection. Now that angle of incidence that causes the angle of refraction to be 90 degrees, we call that the critical angle. Anything less than the critical angle, any angle of incidence less than that, will cause the light to refract. It will come out into the other medium. So in this case, anything less than the critical angle, the light will always end up going into the air. Anything at the critical angle, like it's reflected at 90 degrees, anything larger than the critical angle, and the light is reflected. Now, how can we find the critical angle between any two substances? Well, we already have Snell's law. Snell's law, remember, is n1 sine theta 1 equals n2 sine theta 2, where n is the index of refraction of that material. Now, because I know the angle of refraction here has to be 90 degrees, I can rewrite this as n1 sine theta critical equals n2 sine of 90. I don't know if you remember from math class, but the sine of 90 is 1. So I would end up with n1 times the sine of the critical angle equals n2 times 1. Now, 1 times anything is the anything. So I have n1 sine of the critical angle equals n2. To get rid of the n1, to move it to the right-hand side, I would divide both sides. So the sine of the critical angle equals n2 divided by n1. And then finally, if I want just the critical angle, I have to do the inverse of sine, the opposite of sine. So I end up with the critical angle equals the inverse of the sine of n2 divided by n1. Now, this only works when you're going from a more dense to a less dense material. So if I had tried to put water on the top and air on the bottom and punch that in my calculator, it'll give me an error. I can't have a sign bigger than 1. So your calculator will always try to save you from making a mistake. But N2 is always going to be the less dense material in this equation. N1 will always be the more dense material. Now let's do a problem. So what is the critical angle between water and air? Well, we have a diagram here. Let's label it. Air is less dense. Water is more dense. So we know the light has to be traveling from the water into the air. So the critical angle will be associated with the side of the water. That'll be the angle of incidence. The refracted angle will be 90 degrees. That'll be on the side of the air. Now, from class before, we know that the index of refraction for water is 1.33. So I'm going to write down what I know. We know the index of refraction for air is 1. Remember, it's slightly more than 1, but we've been rounding it down to 1, treating it almost as if it were a vacuum. And then we'll write down what we're given. That is what we were given. We're going to write down what we're trying to find. We're trying to find the critical angle. Now the equation we'll use is the one that I just gave you, that we just derived together actually, that the critical angle is equal to the inverse sine of N2 divided by N1. We'll plug in our numbers here. So the critical angle is equal to the inverse sine of 1 divided by 1.33. After I put that in my calculator, I'll get 48.75. Now remember, on your calculators, for most of you, you'll have to hit that second button, it's in the upper left-hand corner, and then sign. And then put 1 divided by 1.33 in the parentheses. For some of you with newer calculators, you may be able to hit just the sign negative function. So if we look at this problem, any angle less than 48.75 degrees will allow the light to refract into the air. An observer on the other side could see that ray of light. Anything larger than 48.75 degrees would cause the light to reflect back into the water. So if I had an angle of 49 degrees incidence, that light ray will not end up in the air. It will reflect back into the water at 49 degrees. Now let's look at an example of why this, how this plays out in your real life. So why must lifeguards either stand up or they sit in those elevated chairs that are way up above the pool? There's a reason for this. If there's someone in the water in trouble, if I'm elevated above the pool, the angle needed for the ray of light to refract and hit my eye is smaller than the critical angle anywhere that I look in the pool. So I would be able to see a person anywhere within that pool, and find them, know when they were in trouble. Now, if I'm sitting down, that's not the case anymore. So if I'm sitting down, the angle necessary for the light to refract and hit my eye, since I'm closer to the surface, would be larger than the critical angle, depending on how far that person was away from me, if they were on the other side of the pool. So when the light hits, it would reflect back down, and as a lifeguard, I wouldn't be able to see them. Now, I tried to show you what this looks like. This picture on the right-hand side, I know it's hard to see, but if you look, when I'm looking straight down, it's easy to see the tiles. It's easy to see the lines between the tiles, but as you look up, further from you, the tiles start to disappear. This would be the same thing as a lifeguard. And that's because the angle of light necessary for you to see that tile, it's bigger than the critical angle. So it reflects back down. Now here's another example of total internal reflection. I pulled out these pieces of acrylic. They're curved. And when I shine the laser light in them, the light makes it all the way to the other end. But what's happening there? Well, I can assure you that the light is not driving like a car. So the light doesn't move like this ray of light in this picture. What's really happening is that the light travels in a straight line path, just like always, and when it hits the side, it will hit at an angle that's larger than the critical angle. So that means it will reflect in another straight line path. When it hits the other side, it hits at an angle that's larger again than the critical angle, so it will reflect again in a straight line path, and that continues. This is something that's called fiber optic cables. So in a fiber optic cable, the line reflects inside in a series of straight line paths, and the light that was put on one end of the cable will end up coming out on the other end of the cable. Now, you've seen fiber optic decorations before. They're really pretty. But I can assure you that is not the most important application of fiber optics or total internal reflection. Probably the most important application, the one that you use most often, the one that you may be using right now watching this video, is the use of fiber optics to transmit electrical signals. So I shouldn't say electrical signals, but data signals. So the transmitter creates a ray of light. It goes through the optical fiber. When it hits the other end of the optical fiber, it goes to the receiver, and that reconverts it back to an electrical signal, which you're seeing on your computer. Now, the reason that we like to use these fiber optic lines is that they move at the speed of light in glass or plastic, whatever is being used. But they're very fast. Now, another application is cameras. So if I can have light travel through a fiber optic line, and I have a way to view that light on the other side, I could then see things I normally can't. Doctors use fiber optic cameras when they're doing surgery. So on the right-hand side, you can see here are two Navy doctors, and he's pushing a camera into a patient and looking at the screen. So they're actually looking into someone's body. On the left-hand side, there's someone else from the Navy who's inspecting a part. Now, you won't be able to see inside that part, and instead of dragging out heavy equipment like an x-ray machine to see if there's a crack in it, he can do a visual inspection with this camera by putting it inside and seeing what he normally couldn't. So I hope this explains the idea of total internal reflection to you. Have a great day.